Hi, good evening. So, welcome to the last session of the course, Essentials of R Software. I will just start sharing my screen and okay. I think you should be able to see my screen now. Can you just confirm?
Yes, ma'am.
Okay, perfect. All right. Okay. All right. So we've had 11 sessions so far, and this is going to be the last one for the 12th week. So before we start, do you have any question about the course or previous topics or anything?
Uh,
Okay, if not, so we'll just start. And as always, we'll first have uh we'll just be discussing some things, whatever was taught this week, and then we will go on to some practice questions. We'll also be practicing a lot of questions alongside. So if you can keep a pen and paper handy, that'll be nice. And otherwise, anyway, I'll be solving these on screen as much as possible. Okay, so the first things that so the this week was about something called hypothesis testing. So before we go into it, uh, there's this example that was given about depending on how many samples are you looking at. So there are three cases that we will be talking about throughout today's discussion. So either you're looking at one sample. So for example, you're looking at marks of students in one subject, right? So it's like one vector. If you remember the vectors from the discussion in R, so vectors is nothing. It's just a linear list, right? Some 10 elements or 20 elements, some size elements. Okay. There could also be two lists with you. So we'll call those as two samples. Now, the thing is that do both the lists correspond to each other in the sense that is first element of one list and the second element of one list, are they connected in any way? And if they are not connected, then it would mean that you can randomly, then it means the order does not matter, right? But in case if there's some sort of a connection, then there are two things which you can understand from there is one, the number of elements in each of these lists is going to be the same, right? So suppose we are talking about marks of students in two subjects. So let's say there are 31 students in a class and we're talking about marks in Hindi and English. So you will have 31 marks in English, 31 marks of Hindi, and the ordering is important because if you jumble one, then you also then they don't correspond to the same student anymore, right? So when you're talking about two samples, whether they are paired samples or whether they're independent samples, so we have these three cases. Okay. Does this make sense?
okay.
Yeah. All right. So next we come to this term called hypothesis. So we have been talking about different population parameters, right? So the idea throughout this course almost it has been that there's a population and there is some parameter about the population that we don't necessarily know, right? Something like the mean or the variance typically. We don't know about the population, but what we do is we take a sample out of that population and using that sample, we get an idea about the mean and the variance. And we are typically interested in, we ideally want that the sample mean or the sample variance should indicate the population mean or the population variance. So that's what we are assuming. The other thing that we are now doing in hypothesis is that once we do get some sort of a estimate from from the sample about the population, we would now like to check it with something. We not check in the sense not to check if it's correct or not, but what we want to do is we want to see whether it's related to another term, whether it's some other value that we believe might be true, or if it's lesser than, greater than, something like that. So a simple hypothesis would be something like a fixed value. The value that you got, is it equal to some particular number? We will see examples in a few minutes. But when we are comparing some, so this is a population parameter, and this we are talking about, it's like a belief of the outcome of something. So do we believe that it's equal to 17? That's one case. But if it's not equal to 17, there could be three cases, right? You can simply just say it's not equal to 17. Or you can say it's less than 17, or you can say it's more than 17. So in the case where you know it's a fixed value, then we'll call it a simple hypothesis. But when it's not a single value, but it could be multiple values, then we'll call it a composite hypothesis. Okay. So when we have framed a hypothesis, we would like to test whether the hypothesis is true or not. So now there could only be two outcomes. You have a hypothesis. So a hypothesis, you've said that, okay, something is equal to something. And if it's true, that's one option. The other option only is that it's false. So you either accept the hypothesis or you reject the hypothesis. That's the only thing. Okay, so it's accepting or rejecting hypothesis. And so now we'll just look at some, like, a proper definition of the whole thing. But just a second. Yeah. So we'll also look at this proper definition, but we'll mostly be interested in the direct application of this. So the notations that you see here are not, they might not always come up in the upcoming questions. So okay. So what we are doing here is we have some sample. So we have n observations. Okay. So n is the sample size. We are defining two disjoint sets. We are defining two events, theta naught and theta 1. So this one is like a theta 0 or theta naught. And whatever you observe, it can either belong to two possible options. It may be event theta naught or it may be theta 1. And typically what you are calling as theta naught is your H naught or the null hypothesis. Okay, so this is what we are calling as the null hypothesis. And if it's not null, then the other option only, then it's the other option, right? So another term for other is alternate hypothesis. So your case needs to fit either of these, right? There's no third option. If you define null hypothesis as equal to 17, then your alternate has to be that it's not equal to 17. Okay. Now what you need to do is, so these are our observations, right? Now the observations will belong to a certain region. Again, we are defining two disjoint regions. One is called C, which is the region of rejection or the critical region. And the other one is C star, which can be called like the acceptance region. So again, these are complicated notations. These will not come up so much in the upcoming questions. But so what terms you need to know is that there is something called the null hypothesis. And the null hypothesis corresponds to the C region or the critical region. Right? And C star, which is the acceptance region, then you accept H naught. Now, as we will also see here, we'll just see it in a while as well. Typically, the way these questions are going to be solved or the questions are going to be framed is that the first step is going to be to define the null hypothesis. And then the solution, the next step is going to be whether you accept H naught or you reject H naught. That's going to be the main thing. Okay. All right. So now you defined a hypothesis that it's equal to something or it's not equal to something. So you define something. Now let's say in an ideal situation, you know which of the two cases is true. So there's something called the reality. This we don't know, but we have, but calculations have been done for this. So there's some reality which can be that actually your null hypothesis was true or actually your null hypothesis was false. Now, you as the person who's doing this calculation will either accept the null hypothesis or reject the null hypothesis. Now, if you accept the null hypothesis when it's actually true, then it's a true positive. Okay. And when you reject it when it's actually false, then that's also the right thing to do. So you call it the true negative. But when you reject it when it was actually true, so you rejected it. So it's a negative result, but it's not the correct negative. It's a false negative result. And this thing is what we call as type 1 error, this alpha value. And likewise, there could be case when it's actually false, but you accepted it. Okay, so that's going to be the false positive. You accepted it, so it's a positive result according to you, but in reality, it was not the right thing to do. So this is the type 2 error, beta. Again, size of type 1 error, as we saw in the last slide. So alpha here is actually the size of the critical region. Okay. And beta is the opposite. Power of the test is 1 minus beta value. So basically the true negative. So these things, these are just values. It'll be nice if you can remember this table. It's actually not so much to remember as much as to understand that when do you call something as a true positive and a true negative. Okay. So again, alpha, beta can be values that you would like to calculate. Okay. And we will see a couple of examples for this also. All right. So, and continuing from these alpha and beta values. So generally the way H naught, so you start with defining H naught, the null hypothesis. So H naught is defined as the case when nothing new is happening. So there is no difference, something is equal, right? And then H1, which is the alternate hypothesis, so it's also called H alpha or HA sometimes, when something new is happening, and typically that is what you are interested in. But you start off with H naught. So it's a slightly opposite thing to do. You are interested in H1 or the alternate hypothesis, but you calculations are all done in terms of H naught. Okay. And now, so we assume that H naught is true and we test this for acceptance or rejection. And now these two errors that we saw in the last slide, so alpha and beta. Now both of them, ideally we would want both of them to be as small as possible, but that cannot happen. So what can be done is you can fix a certain value of alpha. You can say that, okay, maybe this much alpha is acceptable. So we'll fix this. And then you would like beta to be as small as possible. And we'll see how that happens. So again, the same thing that we have been looking at so far. The area of the critical region is alpha, and the area of the acceptance region is 1 minus alpha. So acceptance and rejection of the null hypothesis. So now this plot that you see here, so this is a normal distribution, right? We've seen this. Now we know that the total area under this curve is equal to 1. So if I say that the acceptance region is 1 minus alpha, so let's say it's somewhere in the middle. So the remaining parts, the left and right, they are equal to alpha and it's symmetric. So each of these small areas that you see here at the edges, they're both alpha by 2. Okay. So this is important. So when we are talking about this thing called the two-tailed test, since there are two ends and we want the total area of the two ends to be equal to alpha, the individual areas are going to be alpha by 2. Okay. So that's something you need to remember. On the other hand, when we're talking about just one-tailed tests, one-sided or one-tailed, whether this tail is on the right side or it's on the left side, then there is just one shaded area that we're interested in. So that's directly equal to alpha. Okay. So now each of these questions, we will have two ways of looking at it. One is when you're manually doing some calculations and you would like to see where is so we'll see it in the upcoming slides, but we'll calculate a test statistic as we have seen in some of the previous weeks, whether it's the T statistic or the Z value or the F value. We will calculate some value and we will see where it's lying here. Is it lying in the shaded region or it's not lying in the shaded region? That's it, right? As simple as that. That's one way. The second way that we are going to be doing is, which is normally done by the R software, is that it's going to give you a p-value. The p-value is the probability of rejecting the null hypothesis. Okay. So And so the p-value has to be really small. And then we're going to reject the null hypothesis. There's another thing in terms of the confidence interval, but it's not explored so much, so I will not confuse you with it. But right now we'll be solving the upcoming questions in two ways. Okay. So fine. So this is sort of like a cheat sheet for you. These are the cases that we'll be talking about in the upcoming slides. These are the cases that were talked about in the weeks, whether you're doing a one sample test or a two sample test for the mean, or it's for the variance, and what is known, what is unknown. So I have put in a few things here. I'll not go through it right now. This is for your reference. We'll take on examples and questions one by one. Okay. The distribution was actually so the derivations of what all was done is explained in depth in the lectures. So maybe what I'll just do is, so I'll just quickly go through it and then we'll jump on to solving these questions. So when you're doing a one sample test for mean and when you know the variance, then you're simply going to do the z-test. So if you remember, z-test is nothing but standard normal. You're defining a standard normal variable, right? So x bar minus mu divided by sigma by root n, right? So that's a z-test. And when we're talking about the variance, we are talking about the population variance, right? So population variance is known. But now you see, if you don't know the mean of the population, there's a very little chance you'll know the variance of the population, right? You don't know about the population. So a more realistic scenario is the other one, where you don't know the variance. Now, in this case, we would be using, instead of variance of the population, we'll be using the variance of the sample. And in such a case, we do the t-test. But we know that if you have enough samples, t-test almost looks like the t-distribution almost looks like a normal distribution. So we can switch on to a normal distribution if the sample size is large enough. So that's the one sample case. Now, we can have two sample cases also, right? So here is the two sample cases for mean, again, with known variance and unknown variance. And again, in both cases, you can have independent or paired samples. And again, we'll see some examples here. In some cases, the example for paired was given, in some cases it was not given, but all cases are possible. Okay, so it looks like the same thing, z-test and t-test. But now the only thing is that here it was the mean that was following the z distribution, but it's now the difference in mean that is going to follow the z distribution or the normal distribution. Okay. And the last cases that were taken was that it was for estimating the variances. So again, are we estimating the variance of one population, or are we comparing the variances for two samples, two populations? So depending on that, we'll either do a chi-square test or an f-test. Okay. All right. So let's. Okay. Do you have any questions until here?
No, ma'am.
All right. Okay. Good. Let me know in case there's any question, any confusion anywhere. So let's jump into solving these questions now. Let me just grab my notepad here, and I already have the pen with me, so that should be okay. It's working. All right. Okay. So now the question here is, a random sample of size n20 of the day temperature in a particular city is drawn. Let's assume that the temperature in the population follows a normal distribution with sigma square equal to, so this is one value and this is one more value, and we have this sample. Okay, so keep an eye out on what's a population, what's for the sample, right? So this is the sigma square. As we denote, sigma is always for the population. So sigma square is 36. So sigma is 6. And this value that you see here, this is the sample. And the sample mean is given to you in this question. So now you want to check what is happening. Like, can you say that the mean of this population, so this is the mean of the population, right? And this is the mean of the sample. So you want to see whether they're equal. Okay. So the way it's going to be solved is we define the z variable. We will define this as x bar minus mu divided by sigma by root n, right? Now, if you solve this, it's going to be 4.97 minus 30 divided by 6 divided by root of 20, right? So now I do have it solved with me, right? So take my word for it. And this comes out to 8.93, okay? So you subtract this, so it's going to be 11. It's going to be 6 by something around 4. So it's going to be 1 point something. So 11 by, let's say 1.5. So yeah, something around 8. Okay, fine. Now, what do we do with this value? Okay. So what we can do now, okay, this, I'm going to keep this. So now this 8.93 is this death statistic. Now we just saw a couple of slides back that we are interested in whether this statistic value, is it lying in the shaded region or is it not lying in the shaded region? Okay, so to identify that, what we'll do is, if you remember this page here, so we want to check what these critical values are, where all is the shaded region occurring. So what we are going to do is, let's say we are doing a two-tailed test. So we want to see either cases. So there's this option right here, okay, twice of this. Now we want to check 0.05, right? We are defining that area of that shaded region, the critical region is going to be 0.05 or 5%. So when I press enter, you see this is what comes up. You can see these two values here. This is equal to 1.96. So this is 1.96 and here it's minus 1.96. So you now know where all the shaded region lies, right? The value we got here was 8.93. So definitely this value is somewhere here, right? So it's towards the shaded region. Now, when we know when something is in the shaded region, that's the region of rejection. So what we need to do is we need to reject the hypothesis here, right? So the hypothesis was that the population mean is 30, but we can successfully reject it, right? Now, this was one of the three cases. This was the case of two-sided tail, two-tail test. Now, we can also have this one-tail test, and we'll write this as, now just one of the ends needs to be 5%. So here in this case, the value is 1.64. Likewise, we can take the opposite side also, 0.05. So it's minus 1.64, right? So you now know where the shaded region is beginning and ending. So in either case, so in this case, of course, we are going to, so here our value, which is 8.63 or 8.93, it's not lying in the shaded region, right? So we can say that the population mean is not less than 30 at least. That is what we can say for sure. But greater than 30, well, it is going to be greater than 30, right? Does this make sense?
Okay, ma'am. So we will be accepting the H naught in third case
We will be accepting H naught in
in
the
third
third
case.
case. Yes, that is the population, that mu is greater than 30. That we will accept.
Yeah. Okay.
Yeah. Right? Because mu is less than 30, that we'll reject. Yeah, mu less than 30 we'll reject and mu greater than 30 we'll accept. Okay?
Okay.
All right. Okay, fine. Likewise, we have another example here. So here also a survey was done and they found that the average annual salary was this. So 10 years. So this was 10 years ago. And then, so this is sort of your population mean or mu here. Now a sample of 112 CAs gave a mean of this thing and a sigma is given to you. Again, it's the same question, right? You now have sigma, you have n, you have x bar, you have mu. Again, you can do the three cases? Right? Would you like me to solve this? Okay.
Okay.
Yeah, okay. Before we do that, I think for the first question, we can also solve this in R, by the way. Okay, so what we are going to do here, I hope I already have this with me. Yeah, okay. So this is the vector that we just took a look at, right? We had these 20 numbers here. So it's exactly the same thing that we have seen, right? 20 numbers, and the mean of this one is 4.97. Now we want to check whether the mean is equal to 30 or not, and the standard deviation that's given to us, right? Variance is 36, so standard deviation is 6. This is what we've been given. So now if you want to do the three cases, we did it manually also, right? We calculated the Z statistic, the Z value, and we saw whether it's lying in the shaded region or not. Likewise, we can also do it in R. We have this function called Gauss.test. We give the vector, we give the mean that we want to check, we give the standard deviation of the population, and we have cases like alternative, less, and greater. So when it's two-sided, so the value that you see here, this is the important value, the p-value. If the p-value is smaller than 0.05, we will reject the null hypothesis. Now this value here, that is less than 0.05, right? So this notation here means 1 into 10 to the power minus 6. So it's 0.00001. Yeah, like 5 zeros and then 1. Okay. So it's a very small value. So it means that the mean is not equal to 30. The null hypothesis is that it's equal to 30. So the alternate in this case is that it's not 30. So you will reject the null hypothesis. Right? In the second case, again, the null hypothesis is that it's equal to 30, but the alternate is that the value is actually less than 30. Now you see here the p-value is very high. It's the highest that's possible. So you cannot reject the null hypothesis. You cannot say that you cannot accept the alternate now, right? So it's 30 or greater. Lesser is not possible. You cannot accept the alternate hypothesis in this case, right? So you don't know whether the mean is equal to 30, but you know that for sure it's not less than 30, right? And likewise, when you're saying it's greater than 30, then the p-value is very small. So you can reject the null hypothesis. So you can accept the alternate hypothesis. So both the things. In one case, you were calculating the statistic value and you were seeing whether it's lying in the shaded region or not. And the other way is via the p-value. And both of them are giving us the same answer. So that's good. Right?
Okay.
Now this question here, if we get time towards the end, we can solve this again, but it's going to be exactly the same question. Right? You have the same values. It's just for your reference. I've sort of collated all the questions that were there in the lectures, but again, it's the exact same question. Okay. Now the only thing is here you don't have this sort of a vector with you, right? You don't have this vector, so you cannot solve this via R. You can only solve it manually, right? But when you solve it manually, it's going to be something similar. And if you solve this, you would get, so let's say if you do solve this, you get a value of the Z statistic to be 2.71. So can you tell me in what case? So where is it? Yeah. So if you solve this, you'll get Z is equal to 2.71. So this is your normal distribution, right? This is where minus 1.96 is. This is where 1.96 is. Now you can see that 2.71 is going to lie somewhere here, right? So it's lying in the shaded region. So is are the sample mean and population, is it equal to, so let's say we are talking about this case here. So are you going to accept the H naught, or are you going to accept H1?
We want to reject H naught.
Perfect. Right? So reject H naught. All right, cool. Fine. Okay, I was supposed to solve it here, but I've solved it in the previous slide, so that's all right. Okay, now the second sort of an example that we are looking at is for the mean with a unknown variance. Now you see it's the same question, but now you don't have this value given to you. Right? So now what we're going to do here is we would instead, so we'll do the t statistic. We now need x bar minus mu divided by s upon root n minus 1. So now this s here is actually the sample standard deviation, right? Sample SD, that's equal to S. So you can do it manually, but just for making it quick, I will do this via R. So the standard deviation is the square root of the variance of this vector, right? So we get 6.07. So this is equal to 6.07. That's it, right? So now what we're going to do, now here, the previous case, this mu was 30. In this case, just to make it different, it's 40. But calculation is still going to be of the similar type. So we want, so, and the mean we just saw, right? X bar we saw in the previous slide, it's the same thing, 41.97. So the way we're going to solve this is 41.97 minus 40 divided by 6.07 upon root of 20. Okay. We're going to solve this. It would be roughly around 1.4, 1.47. Okay. Now, can you tell me what we are going to do with this value?
We
Now,
are going to compare the three cases.
yes. So we need to identify where the critical region is going to lie. And now you see the size here is 20, right? So we need to use the t statistic. We need to use the t distribution. We cannot equate it to the normal distribution. So we'll go on to the t distribution thing. And now t distribution depends on something called the degrees of freedom. And for this case, we are looking at degree of freedom is equal to n minus 1. So n was 20, therefore degree of freedom is 90. Okay. And let's say we want to take again the greater than less than two-sided case. So you want the two-sided thing to be equal to 0.05. We got this. So the value of the critical region here is 2.09. Okay. So again, t distribution is also a symmetric distribution. So what is happening here is this is 2.09. This is minus 2.09. And this is your critical region. 1.47 lies here, right? 1.47. So it's not in the critical region. So not reject H naught. So you accept H naught. So you can say that, well, now you can see here, right? Just for a sanity check, you estimated 40.97, sorry, 41.97. You are comparing it with 40, and there is a small standard deviation, right? So 6, it's a substantial standard deviation. So, which is why 40, 41, they are good estimates, right? So you are not rejecting that mu is 40. So you can actually say, yeah, mu, quite likely mu is 40 here. Okay.
Okay.
All right. Next, we come on to the other case. Now, what we want to do is, we want to compare two means to each other. Okay. And the variance of the population is known. So here we have one sample or one sample from two different populations. The standard deviation, let's say it's known to be 2, and we want to check here if the two diets are different from each other or not. So the null hypothesis, as you remember, we define it as the simplest case. So we say that nothing's different, everything is equal. So null hypothesis here is that mu1 and mu2, they are both equal, right? So now, by the way, the standard deviation, okay, so I have this formula written here. So what we do is we use this thing. So what I hope you can see this. So what you're doing is the numerator is the difference in the two means, the difference in the two sample means, and the denominator is like a weighted average of the population standard deviations. So it's sigma 1 square by n plus sigma 2 square by n, and you sum them up and you take the square root of that. Okay, so I think it's better if I solve it here so that we have these values with us. Okay, so what we are going to be doing here, we want to calculate, first of all, we need x1 bar and x2 bar, right? So x1 bar here, if you calculate this again, it's a simple arithmetic calculation, right? You just add them up divided by the number. By the way, this here we have 12 observations and here we have 15 observations, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is 15. So x1 bar is going to be around 28 and x2 bar is going to be 30. Okay, 30 and this is 28. This is equal to both sigma 1 and sigma 2, right? Both of them are the same value. So now we want to calculate this thing, right? So what we want to do is we want to do 28 minus 30 divided by, so sigma 1 square, that's 4, 4 by 12 plus 4 by 15 whole root. You solve this up, you should get, it should be minus 8.33. Okay, I hope I've solved it correctly. But yeah, so this is what the value you get. And again, you want to do the same thing, critical value, right? And you remember for the critical value, this is normal distribution. So it's going to be 1.96 here and minus 1.96 here, right? Minus 8.33 lying somewhere here. So again, you have to reject H naught. Right?
Yes.
Okay. And we can again just double check this in R also. So I hope I have this with me again. This one we already saw. Okay, so again, yeah, these are the two values, vec1 and vec2. Now we want to check for the equivalence. So yeah, so now you see here, the p-value is really small. So when the p-value is small, you reject the null hypothesis. It's less than 0.05, right? So same thing. That's exactly what we've been doing so far. The second case right here. So again, it's the same pattern. Sorry. So here you have this as n1. This is equal to x1 bar. This is equal to sigma 1. Then here you have n2. Here you have x2 bar. This is equal to sigma 2. Again, same thing. You'll do the same calculation. So when you do the whole thing, then the value of this z statistic, it again comes up to be 8.82, this time positive. But again, you know it's going to lie somewhere here, right? So again, you're going to reject H naught. Yeah. Okay. Cool. Are we good till here?
Yes, ma'am.
All right, cool. Okay, we do have a few more people who have joined us. So, welcome. Good evening. We're just solving some questions from the topics that were covered this week. And we can just, so it's sort of this, as this part is independent of mostly what we've been talking about until now. So, you can join us now. All right. And let me know if there's any question, any doubt. So again, this is just an empty slide. Okay, the next case that was talked about is, again, we are now comparing means to means, but let's say this was this case. So now we are talking about where we don't know the population variance, which is again a more realistic scenario. When you don't know the population means, it's quite likely you also don't know the variances. So now here what we do is, um, we, like we did in the previous, in the one sample case, we have to calculate a common, uh, like an averaged out sample means. So now it's going to be the single value sample variance, sorry, not sample mean, sample variance, and it's going to account for the variances of both the samples. And the test statistic that you see here, it's going to be slightly complicated. So it's, the numerator here is the two difference of the two means, and the numerator here is that sample standard deviation and some combination of n. So n and m here is dictating these values. So that's 12 and 14. But you can see it's a slightly different, slightly difficult calculation. So here we will prefer to solve this in R. Okay, you can do it manually, but it's going to take you longer, right? But again, if you do want to solve this, it's the same funda as before. You calculate the value of s square. You take the root, so you get s. You plug these values here. So x bar, you know, that was 28. Y bar, you know, that's 30. M here is 12. N here is 14. So you, once you plug in these values, you get this value of the t statistic. Once you have that value, you need to see, again, you need to identify where the critical region is. And here, the degree of freedom, right? So for the t distribution, degree of freedom is important. So degree of freedom is equal to m plus n minus 2. So in this case, that's equal to 24. So 12 plus 14 minus 2. So that's 24. So based on 24, you can calculate the position of the, um, where the critical region is lying, and then you can see where the t statistic is with respect to that critical region. So, but again, like I said, it's better we solve this in R. So in R, it's going to give us, it will give us the t statistic actually, but also it's going to give us the p-value, and it's a simple judgment when you get the p-value. If the p-value is small, if it's smaller than 0.05, you reject the null hypothesis, otherwise you have to accept it. So I will get on to R in just a minute. So when we're talking about two samples, we can also have a case where the two samples are paired, right? So for example, one of the cases, well, the simplest thing is, let's say we're talking about um, students in a class, and we're talking about two subjects. So for each student, you'll have two subjects, right? For roll number one, you can have marks in subject one and subject two. Then for roll number two, you'll have marks in subject one and two. So it's very similar to this table. So let's say this is the student one, marks in subject one, subject two, again, like that. Or it's often like before and after of something. So the order is important. You cannot jumble one of the columns and the second column can stay the same. That doesn't happen. In case of independent samples, that can happen, right? So you see, there's no order important here. Even if these were jumbled up, you'll still get the same answer. But here the ordering is important. And by the ordering and how we take into account that ordering is, we calculate something called the D value. So what we do is, D is nothing but the difference. So it's going to be 2, and it's going to be 14, and then 1, and then 0, and then 4. And now this is the, now sort of this becomes your single sample. You forget the older samples. Now this becomes your single sample case. And it's the same case as the single sample mean with no variance, right? So this case, This one sample mean unknown variance. So it becomes the same thing. So when you have fewer than 20, you use a t-statistic. And again, the degree of freedom is going to be n-1, so that's going to be 4 in this case. Again, you do the same thing. You calculate standard deviation, you get a t-statistic, you see where the critical region is, and you get the value. But since, again, it's slightly complicated question solving here, so I will recommend that we, for the purpose of this one, we'll solve it in R. So let's go there and solve this in R. Okay, so we have this case. Right, so we had this two sample test for mean when the variance is unknown. Right? So this was the first case, the one on the left side, right? So we can, once we solve this, so now you see it's going to give us the value of the t-statistic. Here the degree of freedom, whatever the internal calculation is, it's not giving us 24 exactly, but you can ignore that for now. I'm also not entirely sure what the algorithm does, but nevertheless, it's close to 24. And so this is the mean that we anyway calculated for the two samples. And the p-value here is, it's a large value, right? It's greater than 0.05. So what you can do is you would have to accept, you cannot reject the null hypothesis. You need to accept the null hypothesis, right? So that's it. You cannot say that the two sample means are different. They are actually the same, that means, right? So 28 and 30, since you don't know what the standard deviations were initially, so you can't say that they're two different values. You need to accept. Okay. So this was the case. The second one where we are looking at these paired samples. So I have these defined here, YA and YB. So here I'm doing a t-test. So again, specifying YA, specifying YB. Since we are looking at the equivalence, we're going to say mean is 0. And we are saying that these are paired samples. The alternate, let's say we're taking the two-sided case. So if you actually take the mean of the two values, it's going to come up at 6.6 and 2.4. So the mean difference is 4.2, which is quite a lot of difference. But the thing is that you have very few values, right? And you can see that the variances, so they do have quite large variances as well. So when all of that is taken into account, even though that difference is 4.2, you cannot say that the difference is significant, right? The p-value here, that's very large. It's larger than 0.05. So you need to accept the null hypothesis. The null hypothesis was that they're equal. So you need to accept it. Okay, so in both cases, you are accepting the null hypothesis. Are we good till here?
Yes, ma'am.
Okay, so we will accept H naught in both cases. All right, okay. So these were the 4 cases for testing the mean, right? 1 sample test for mean with known and unknown variance, and 2 sample tests for mean with known and unknown variance. And then we'll come on to the 1 sample test for the variance and the 2 sample test for the variance. So again, 1 sample test simply means you want to check whether it's equal to some value or not, right? So it's the same example. You don't know the mean of the population. But here what you're going to do is you'll be calculating the chi-square statistic, which is n-1. So that's 20 minus 1, 19. And yeah, and S square is going to be this. S square is what you're going to calculate here. So n is equal to 20. S square, that's equal to, you'll do the variance of this vector, right? In R. So I think I have the value calculated with me. Do I have it? Yes, I do have it calculated. So that's equal to 36.85, right? And sigma square anyway, that's 36, that's given here. So you calculate the value of this chi-square statistic. That's equal to 19 into 36.85 divided by 36. Now, even if you don't calculate it perfectly, you can see this is almost equal to 1. So this is roughly equal to 19. Okay. So even if you don't have a calculator handy, this is simple. But yeah. So now what we want to do is we want to do a two-sided test, right? But now remember that chi-square is not a symmetric thing. Okay. So chi-square looks something like this. And it's no longer about 0. So what we are going to do now, so let's go here, let's go here. Okay. So now we know degree of freedom, that's equal to 19. So this is what it looks like. So what we are going to do is we are going to split this. We'll say 0.025, right? 0.05 is the total thing. One side is going to be 0.025. So the right side here is at 32.8 and the left side here is equal to 8.9, right? So 32 and 8.9, these are our limits. And the value that we got here was 19. So let me just write it again. Okay, pen. So this is something around 9. This was something around 32, right? So 19 is lying somewhere here. So this one, so this is your critical region. So this is in the acceptance region, right? So you need to accept the null hypothesis. And it makes sense, right? You got 36.85. You were talking about 36. So they are roughly the same value. Okay. Cool. Fine. Now we come on to the last case where we have two sample tests for variance. So now we want to compare whether the two, whether the variances of two populations, whether it's equal or not, right? Whether the variances differ or are they the same. Now here, what we are going to do, we use the F statistic. And again, it's a slightly complicated formula. So what you can do instead, I mean, you can plug in these values, but I would much rather like you to solve this in R. Okay. But yeah, again, if you do the F statistic, if you actually do it properly, you'll get 2 degrees of freedom, right? For first and second. So that's, so n minus 1 and n minus 1, two values. So you have like, let's say there were 30 values tested in each case. So 30 minus 1, 30 minus 1. So 29 of those. But yeah, again, this one is going to be better solved in R. So we'll just compare this. And the way this is done is that you do this two sample test. And the formula, the command that you use is var.test. Okay. By the way, I think I missed this. So when you do a one sample test for variance, the function is var test where t is capital. Okay. But when you do a two sample test, it's var dot test, everything in small. So again, it's slightly, it's just extra information, but yeah. So what we are doing is we have these two vectors. We've already defined this. We want to compare the ratio. So the null hypothesis is the ratio is the same. So they're equal. So the ratio is 1. Then you can just specify alternate hypothesis. And when you run this, you'll get this value. It does the F test. This is what the variance comes out to, the ratio comes out to be. And depending on how many degrees of freedom you have and all of that, you get a p-value. Now the p-value is large. So you cannot reject the null hypothesis, right? You have to accept it, right? Okay, so that's pretty much it. Um, this is again saves for solution. Now, I do have a few more questions which are very similar to the ones you have in your assignment. Um, so let's go through those anyway, right? So what we can do is we can try to um solve some of these at least. Okay, so this one is important. Now, an experimenter is testing some hypothesis. It's a slightly different way of defining the hypothesis. Normally, we have a different way, but here, oh, I'm sorry. Okay, yeah. Here, this is the way we are defining the hypothesis, H naught and H1. And it's based on 15 Bernoulli trials. And the decision rule is to find out the value of the t statistic as the total number of observed successes. And we accept the null hypothesis if t1 is greater than 11, or else we reject the null hypothesis. Now it says we want to find out the value of the type 1 and type 2 error. So first of all, you want to calculate alpha and beta. That's the main thing. Now, if you remember what alpha is, so alpha is that we want to reject H naught, but it's true, right? Likewise, here we want to accept H naught, but it's false. Okay. Okay. Now, so let's say we'll take this case. So this is equal to alpha. This is equal to 1 minus alpha. Okay. Now, do you remember this function p binom? So it's so anything that was this p binom, p norm or whatever, this was for the CDF. And you remember CDF is basically probability of x less than a certain value, right? So it's always towards the left. Now, let's say we are making this plot for H naught. So basically we are making this plot when this is equal to 0.8. We're taking that case first. So what we're doing here is we're defining theta is 0.8, and what we want to do is, what is the case that we are rejecting H naught in? We are rejecting it here, but it's actually true. So this is the area, right? Mm, 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 mm. Yeah. So this is the area where it's actually supposed to be true, right? So H naught is true in reality. So that's equal to P binom. And if you remember P binom, the way it works is that you'll have to specify the value of the number of successes. Then we specify the total number of trials, and then we give the probability, which is equal to 0.8 in this case. It should actually be this value, right? So it should be 1 minus this value. So this should be yeah. Mm, 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 mm. Oh, wait. Okay. Wait. Sorry. So we won't have this 1 minus thing because we are accepting the null hypothesis when it's greater than 11. Right? This value 1 minus, so yeah, so since it's greater than 11, okay, wait, I think I messed something up. Okay, what I will do is I'll double check this and let you know. I don't think I can convincingly solve this today. Let me double check. Will that be okay?
Okay.
Yeah, because you do have a similar question to this in the assignment, and I don't want to mess that up. So I will get back to you via the discussion forum. Okay. Okay. Moving on. Okay, again, I have sort of collapsed some, like I've just combined some questions which are going to be solved similarly. Um, just to save on time, because there's no point in we just keep on solving it unnecessarily in the same way. So let's see. So we have 70 weighing scales, we have weighing machines that, so again, it's, sorry. So okay, this one looks like this is a value n, right? This is some sort of an average. So that's going to be x bar. This is standard deviation. It's this again. You have null hypothesis and alternate hypothesis. So it's the first case. So you'll calculate a Z statistic. And if you do solve this, the Z value is going to come up to 13.97. Right? Again, if you remember, this is only 1.96 and minus 1.96 when you're talking about the two-sided case. And when it's just one-sided case, right, then it's equivalent to 1.64 or something like that. 1.64 or 1.65. So either way, uh, x bar, yeah. So you have to, so when this is the case given to you, you will be able, you will not be able to reject the null hypothesis because the value is lying here, right? 13.97 is lying here. So you cannot reject the null hypothesis. Right? Likewise, you can do it for the second question as well. This is equal to x bar. N here is going to be equal to 5. Mu is this. Sigma. Okay, so this is the case where sigma is not known. So instead you'll calculate S from these 5 values. Right? And you'll do the T statistic here. You can also solve this via R. Okay? Let me know in case you want me to solve any of these questions in detail. But otherwise, they exactly are the same way that we've just seen in the previous slides. Okay? Likewise here. Yeah, so again, this fourth question is very similar to the previous question that we just saw. Okay. Again, this is equal to n. This is your sample. This is equal to mu. You can calculate x bar from here. You can also calculate s from here. So if you calculate the mean here, you'll get 353.8. If you calculate x bar, so s from here, you're going to get 21.85. Solve the whole thing. You get this t statistic. It's going to be equal to 0.777 something. Okay. And we would like to make the degree of freedom as 19. You're going to see this. It's going to lie, it's going to be 2 point something, 2.09. It's going to be minus 2.09. Again, the way I solved this, I used it in that the web page that we are looking at, right? So you can just search that web page as normal distribution calculator, t distribution calculator, f distribution calculator, chi-square distribution calculator. So you get these applets. I'll anyway share the link. I'll add the links in the slide. So anyway, so you get this value. Now 0.77 is going to lie here. This was your critical region. So you cannot reject. You can also solve this in R, by the way, because these values are given to you. So you can calculate this. You can solve this in R also, right? Likewise, same question here. Okay, it's the exact same question. Okay. All right. Now this
Excuse me,
look,
ma'am.
yes.
Ma'am, can you please teach how to look at the T table?
Okay, sure. Yeah. So I am not using the T table, by the way, here. I am okay. So what we'll do is, okay, so let's go here. Okay, so for this question, the first thing that we do is we need to calculate the degrees of freedom that we are interested in. And for the calculation that we are doing, that's equal to n minus 1. N was 20 in this case, so n minus 1 is going to be 19. I'll I'll the first thing I look at is the degrees of freedom. So that's 19, and I press enter. So it's going to give me a t distribution. Now, depending on whether I want a lower tail or an upper tail or a two-sided thing, I'll select which case am I looking at, what area am I interested in. So the way, so in case you missed the initial discussion, the idea is that the critical region, or in the case here, so here when we are looking at this thing, the critical region or the area of rejection is always going to have the area alpha, irrespective of which of the three cases we are looking at. Now, if you're looking at a one-sided thing, the single area is going to be alpha, right? On the right side or the left side. But if you're looking at this two-sided test, the total area is going to be alpha. So if you're looking, so irrespective of whether it's a symmetric distribution or a non-symmetric distribution, the left and the right areas are going to be alpha by 2, both, always. Okay? So now in this case, what we can do is, so twice of that area is going to be 0.05. I'll just write 0.05 here. I'll press enter and I get this value here. So it's 2.09 here and minus 2.09 here. Just to double check, what I can do is, I'll take this value. If I write 0.025 here, it still gives me the same thing, right? So the right half, if it's 0.025 in area, then it's at it's 2.09. But if I'm looking at a one-sided test, then the total area has to be 0.05 just on the right side. So then that critical value starts from 1.73. Let me just anyway put these values, these links here.
Ma'am, is it possible that you can search for T table on the net and then
Okay, sure. Okay. Table statistics. Okay, let's say we open this one here. Okay. This looks okay, right? Okay. So now, okay. So let's say we're talking about this two-tail test. Now, alpha, typically we are always interested in 0.05. So which is why they've given it green. Now you see here, degrees of freedom, we were looking at 19, right? This thing. So we go here and we check it's 2.09. And it's a symmetric distribution, right? So, again, same thing. Right? So you see 2.093. This also says 2.093. This is for two-sided and this is for one-sided. Did this make sense?
yes, ma'am.
Yeah? Okay. All right. Cool. Likewise, you'll have the table for normal distribution, F distribution, chi-square distribution. Give it a try. I will still recommend that you use these things to get a better, like a figurative understanding of this thing, a graphical understanding. Okay. But yes, that makes sense because you'll be given T tables instead in the class in the exams. So you should have an idea on how to look at it. Okay. So yeah, so you'll have this thing for normal distribution. This is going to be for distribution, and we have this for the chi-square distribution, and we also have this for the F distribution actually. So I'll just write the F test distribution calculator. Oh, not T test, F test. So it's this one. Yeah. All right, good. Looks good. Where were we? Okay. All right. Now this question here, it's a very lengthy question. It looks very lengthy, but try and see what we are doing here. Long story short, we have something called sigma alpha and sigma beta. We also have two distributions given to us, so we can definitely calculate. So we want to. The hypothesis is that there's no appreciable difference in the mean life. So we can calculate x1 bar. We can calculate x2 bar, right? So if you do calculate that, so where is it? Yeah, this one. If you do get this, it's going to be 61.65. And you calculate the mean of this one, it's going to be 60.025. And you remember this thing right here. It was x1 bar minus x2 bar by root of sigma 1 square by n1 plus sigma 2 square by n2. If you solve this, it's going to be 0.065. Again, this thing, 1.96 minus 1.96. This is going to lie somewhere here. So it's not in the critical region. You will have to accept the null hypothesis. Same thing, you can also solve this in R. Okay, you can use the Gauss dot test thing and give the two values, give the two distributions, and you should be good with that. Okay. Okay. Fine. Okay. Okay. The last set for this bit is this case again, where you have these values, but you now don't have sigma A and sigma B. So the values that you have available in each of these cases. Okay. So you do have N1, right? You do have N2. You do have X1 bar. You have X2 bar. You can calculate S1 and S2, right? You have sample means and sample variances. That's it, right? So it would fall under that case of two samples with and without, two samples without variance. But now you need to be just careful whether it's a paired data set or it's an independent data set. Because if you remember this thing here, so when you're doing a t-test, right? Two sample for mean when the variance is unknown, you can either have paired samples or you can have, in this case, this is the independent or unpaired samples, right? So depending on what the question asks, you can have these two cases. So can you tell me, quickly taking a look, which of these cases look paired and which of these look unpaired to you? So here we are talking about location A and B, right? Here we are talking about medicine and placebo, 12 patients and another group of 10 volunteers. And here we have before training and after training. So which of them is paired and which is unpaired? Again, all the three questions are going to be solved the same way in R. T dot test is the function you'll be using. But paired is true or paired is false? Which is which?
Ninth is paired.
Ninth is paired, right? So, no, sorry. This one. pen. So this is your, so here you'll write paired is equal to true. Here is going to be paired is equal to false. And here also paired is equal to false. Right? So that's it then. Yep, that's it. So this sort of finishes the last, so the Friday's session for the 12 weeks are done with this. You will still have sessions tomorrow and on Tuesday. So in case you do come up with a doubt, you can attend any of those. The links would be shared with you over email as always. For today's class, I will upload the recording and this PPT and the R script on the Google Drive. The assignment is on 17th of April, next Wednesday. And if any of you have registered for the exam, I think the admit cards have been released. And but yeah, in any case, if you do have any confusion regarding the exam pattern or the centers or anything, you can either ask on the discussion forum, or if it's about the like the conducting of the exam, then it's better you can ask the NPTEL team. But I hope there's no confusion on those parts as such. Yep, so that's it from my end. Do you have any questions?
The exam will be conducted on the same date uh, for all the states of India,
Um,
or is it going to
that
be different for
should
different
that I
states?
think there are two different dates in April, 19th and 26th or something like that. But I think you will have to double check given like what's written on your admit card, I think. I have no idea how the exam like how it's going to be conducted, like the technicalities. I think it should be on your admit card, but if not, then I would recommend you to contact the NPTEL team. The email ID, I think it was shared in the discussion forum. To what email ID you
Because
can
I have
contact.
not yet received the admit card.
Okay, I will still say then you can email them and say when you'll receive the admit card. Just inquire it with them. Because I am sort
Yesterday
of
only
not
I
in
got a
that
mail.
loop at all. I have no idea how this is conducted.
Okay, ma'am.
Yeah. Yeah, I think emailing the NPTEL team, not for this course, but the general NPTEL team, I think that will be the most helpful. Okay. Okay. All right. So in case there's no other question, thank you so much for attending the sessions. I think some of you have been joining it. Um, some of like you've been watching these sessions, either the ones on Fridays or others, and I hope this has been helpful in understanding the course. I know it's not been perfect. Lots of scope for improvement from my part, but it was a good experience for me, no doubt. And all the very best for your exam.
Thank you, ma'am.
All right. Thank you so much for joining in. I hope to see you all sometime in some other course. But until then, good luck. Okay. Bye bye then. Good night, everybody.